Hi, everyone. We are going to get started here. This is Neil with IBPSA-SF. It's 6:28, a few minutes early. We're excited today. We have Tianzhen Hong and LBNL here talking with us about a tool that model or simulate occupant behavior in buildings. Very exciting subject. Actually, we always just tell people there is no way to do that. So best of luck. But yeah, it's I'm very excited to hear what you have to share with us today. That's your little microphone there, and yeah.
And thank you for staying late. You are busy and day. So I think, yeah, and thank you for the invitation. Basically, I'm happy to share some of the ongoing research activities, and not just in the U.S. but also there's a large international group, and I think the topic related to occupants' energy-related behavior in buildings is getting some momentum recently, because basically it's that common sense. We're trying to push to net zero energy building. We rely on many really fantastic technologies, but we still see many buildings still have very high energy usage. So we forgot that the human aspect of that. Basically we can buildings don't care what temperature it's about, right? So we found out we're going a long route and now realize we need to look at human more seriously. So this is already the full screen.
Okay, real quick.
Oh, sorry. Let me move
I think they're both last drive.
Oh, okay.
Might have froze.
Maybe F5.
F5?
Yeah.
Yeah. Let's see.
Maybe give me a second. Are we on hold?
Yeah.
Oh, we're not connected? Okay.
Connect.
There's a question from somebody. No, on the left-hand button, there are last one, yeah. The last one. On the icon from the left-hand side?
Yeah.
Yep, this one. Oh, that's fine.
Okay, so
We already started.
audio connected, right? So we're connecting to audio.
Maybe we can just ask whether they can hear us. Right?
Well, there's a chance we're not recording, but
What's that?
there's a chance we're not recording it, but I guess that's so we can see it and they can see us. The webinar folks can see us, but it says until this is validated,
Oh, I see.
they won't start. Oh, there it goes.
Yeah. Oh, no.
I think we should start.
Yeah.
I don't know if we're recording it, but
Okay.
yeah.
Yeah.
Thanks.
So, okay. So I think we all, daily work. So a few questions, and always, like, so I think I mentioned basically, for most commercial buildings and especially office buildings, residential buildings, basically all energy consumed to provide, a working, comfortable, healthy environment for humans. And how energy is used in buildings, So I think in most buildings you have only one single meter. You don't really know where energy is used, and I think now we have smart meters. Just we get better information about when energy is used, but we still know how it is used, right? So I think that some new developments in code may require or encourage to some sub-metering, so you know how much is consumed for lighting, for plug loads, heating, cooling, and fans, and basically get more information, be able to help us understand what's going on in building. I think that's a fundamental before we're talking about how we can save energy. You have to first understand how energy is used, and just like we unfortunately, for a long, long time, we don't realize the value of that. And also how my building compares with others, there's a lot of example shows, I think on one side as well. Even though some of the high-performing buildings, they still shows, very large variations. And how low can the, can energy use for my building? How low can I be? Assume everything was right as, as designed or even better than designed. Indeed, some buildings perform better than building failure. And how to retrofit my buildings. And number 6, interesting because we're talking about energy use, and actually there's 2 different points of that. One is the energy demand, or we call energy service, like what comfort level, how much outside air we need, and then in order to provide those services, right, you deliver. So what's the efficiency of your system? So if we look at these simple equations, right, we're only talking about energy efficiency, but your demand does not change, or it's increasing. You are not going to reduce energy use. That's why you see maybe some buildings have very sophisticated, efficient systems, but still consume lots of energy. And then we also have very aggressive energy goal, like in California, talking about net zero energy building for residential by 2020. So we have like less than 6 years to go. Can we really get there? Right. For commercials in 2030, and it's very aggressive. I think in certain climate, maybe in our Bay Area, probably easily we can do it, but in those hot climate and humid climate, it's quite challenging. So how realistic those goals are, and what kind of policy we should put in place in order to reach those goals. So I think, so these has different aspects related to people's behavior in buildings. So this is a NBI study look at the design performance, simulation. Vertical is the actual performance. So if you look at this portfolio building to simple average, they are not bad. But if you look at individual buildings, right, especially looking those low triangle, those are the low energy use, and basically those are where we want to be. At least that's the direction. But if you look at those, most of the buildings consume much more energy than our design. So you can argue many reasons. Listed some of that. Occupancy can be different. Operation maintenance can be different. Your controls may not be commissioned or working correctly. So there's many reasons. But I think those tend to use more passive, heating, cooling, or human-oriented systems, right? So people can play a much bigger role in those kind of low-energy buildings, and they tend to be more challenging in terms of getting the guaranteed performance. So this is a study we did. We basically compiled about 51 high-performance buildings around the world. Different each bar represents one building. It is color-coded by region. So there's some buildings from China, from Asia Pacific, excluding China, some from Europe, some from US. And so these are high-performance buildings. Basically, each country have their own rating system or using the lead. These are the top, either the platinum or the gold. They're all very top. But if you look at their EUI, you can see it's just a huge spread. And it's not just across the whole world, but also within a country, it's also quite spread. And so I think it's a good question we asked before. So basically, sort of the top question again is, so what strategies to support design operation so that we can really get to high performing buildings. So I tend to look at all these main pieces here, right? I mean, there's many on top technology. So we are working on a lot in those areas, but operation maintenance is important. Sometimes more important, and whether we use integrated design approach at the beginning or even the life cycle of the design process. And there's a building usage, so that relates how people interact with the building systems, and it's the other on the left side is all the policy related, applying standards, energy code, labeling, how they promote or regulate the market. So on the right side, so if you broadly define operation, integrated design, usage, they're all related to people and how people practice or behavior has significant impact on building performance. So some background of the behavior research is, so basically technology alone not necessarily will get you to low energy building. So there's many examples shows that. And human behavior basically can play a positive role. So we tend to design everything automatic, try to get human outside the loop, right? People tend to mess up things, but there's not data to support our understanding, how people actually behave and how it can be positive factor. So we do lots of modeling. We way simplify behavior, so we don't really be able to look at its impact, on the positive side. And there's some study shows that just some behavior change, and you can have significant potential to save energy. And for low energy buildings, it can be very significant. But behavior is very complicated. So it's a lot of uncertainties because different people can behave differently. Even the same people can behave differently at different times of day, different day of the year, and so there's a lot of driving factors like we talk about individual culture, lifestyle, your personal habit. Depends on your environmental awareness. How you care about global warming, global climate change, or you think there's somebody else's business. And of course it also depends on time. The temporary factors like time of day, day of the year. It depends on where you are. Like you may behave differently in office or at home, right? I mean, obvious difference is in office normally you don't pay the bill directly, but home you pay the bill, so you may more care about energy. And there's also lots of actions depends on indoor and outdoor environmental conditions like temperatures and CO2 and bunch of others. And so there's very limited data to help us understand behavior, people's behavior in buildings. So this is an example on operator behavior. So if somebody complains, it's too hot during summer, assume it's a VAV system, right? So the operator may check other people. Maybe other people are fine. So it's just you complain. So you will do nothing. You're very special, unfortunately. And then so maybe it's in this problem, check. Well, VAV box are already fully open, and may have to raise the fan static pressure set point to produce more airflow. If it's partially open, maybe you can override the minimum temperature position, right? But quite often, right, it is something fixed problems, but then they forgot to restore it, right? So it always stuck at those settings, and you probably ended up too much airflow or even reheat. So the idea is then different actions, right, of the operator. We ended up different energy use of the system, and this is for. Also, this is, IBPSA survey how operators address, thermal compliance, and you can see some adjustment of the system components and, adjust the thermostat, and so it's a bunch of, different response, and, it has different implications on energy use of the system. And so for there's also lots of, more and more natural ventilated buildings design operating nowadays, but in the design phase, there's some factors basically we need to consider. There's examples, these kind of natural ventilated buildings in India and China, they will not work because outside air maybe it's just too dusty. You don't want to open the windows. It may be air too polluted. You don't open the windows. And maybe something smells bad. So. And it's sometimes, there's a building in Taiwan, everything's fine, but it's a paper factory, so you don't want to open windows. It can be very noisy, you don't open windows. So I think these are sort of, real world constraints needs to be considered when we design natural ventilation. So some example, this is a graph, from Danish single family house use all the energy use intensities and across different vintage. And there's not real or very convincing evidence that the more recent home will be more efficient. Maybe you can say yes, but not very strong link. So it's not really depends on the the age of the house. And this is a study by Danny Absack. So these are 10 identical homes built on the same year on the same street. But if you look at energy use, it's quite different. I think by a factor of more than 2. So it also has got some breakdown of energy use. Maybe you can look at detail. Maybe a particular house uses a lot of, energy for washing, and in the other one maybe use a lot more for heating and cooling. But basically, it's got a significant wide range of variations. And this is a study done by Tsinghua University, China. So they monitor the cooling energy use by air conditioners during the summer. So this is the building, and then basically these 25 units, right? Some don't use air conditioning at all, and some use quite a lot. So it's a huge range. And there's some further study found out that it's not the people with higher income will consume more energy for cooling. There's not direct link between those. And so basically we look at buildings. There's many, right? We do simulation, or from the design perspective, there's all these driving factors. And so these 3 boxes here, right, related to occupants' activity, indoor environment, what our comfort criteria are, and how people operate buildings, do the energy management is has significant impact on the building performance. So yeah, so we talk about, right, it's a key factor for design, performance optimization, evaluation, and we know very little because we don't have data. Because when we research behavior, it's not something you can do. You can do by survey. Because if I ask you a question, when or how you open window, you may not even know, or maybe you know, but you don't have a clear clue when I open window. Right. So we have to use some real data, and we cannot also put you on a lab. We want to observe your behavior, put you on a lab in 2 weeks, 3 weeks. It will be totally different what we observe from your actual behavior. So there's a real challenge of getting the data, from your actual, environment. And it's also we need these in-depth quantitative analysis models. And there's quite a few groups, about 20 groups all over the world, doing behavior study, but it's very little connections, and so doing sort of insider models may not be used for other contexts, or there's no well documentation of a particular model. Is it applicable to other occupants, other countries, and so we mentioned that. And then so I think to be able to tackle this topic, indeed, it needs to be some international collaboration. So I think we talk about it, simulated and major data. So let's keep going. Yeah, so this is sort of a framework. We are looking at how behavior plays in this overall picture. So there's these comfort cultures that drive the occupants' comfort needs, and then this is how they behave if the comfort need does not meet the requirement, how they react to those. And there's a movement. So sorry, move back. Yeah, so people move around, right? How often they stay in the office, or how long, and actions, they interact with windows, shading devices, lighting systems, or even changing, closing level. Yeah. And so, but there's other factors like psychology, economic factors, some even biology. They can also have, very strong influence on people's, behavior or your comfort needs. Yeah. So basically, it's quite complicated. So what we are trying to tackle, focusing on these, like 3 Ps, because there are lots of others, belongs to different disciplines, and we have some other social scientists, behavior scientists working on these, other pieces. But we are working on these. Basically, we're trying to get data, understand behavior, and be able to develop models to describe those behaviors, so that we can use it in energy modeling, simulation, to look at its impact on design, on building performance. Yeah. So yeah, so there's just a few graphs just to show behavior stochastic uncertain. For example, this is how the air conditioning is used in a bedroom. So these are like day, and these are like different days, right? And this is like turn off, and that is turn on. So you can see every day can be very different. There's no persistent pattern of that. And then the other family also shows, quite random patterns. And so, if you look at, how people turn on air conditioning, there can be many reasons. It can be somebody leave it, always on 24 hours a day. Somebody maybe turn it on when you, arrive home, right? Or you arrive at the office, and then you may turn on only when you feel hot, right? So usually it's a higher temperature than the actual, comfort temperature. You may turn on when before you go to sleep, or never turn on, or randomly turn on. So it's a different modes that people turn on air conditioning. And so if we sort it, for example, we have this many people here, right? They all behave differently. But the idea is that even though it's random and uncertain, we should be able to find certain, patterns. Now maybe pattern 1, we found, 10 people belong to this pattern, right? And so we try to group, discover some, like, for example, we talk about this, turning on air conditioning, right? In the real world, maybe we identify maybe 5 or 6 patterns, dominant these, and we can find how frequently or what is the percentage of a certain pattern, right? Because when we do the simulation, for example, we assume 400 people in this building, we need to know maybe 50% of 400 belongs to pattern A, and then, so basically, so that we can do the simulation. And so our research target, we try to, identify the, this quantitative, definition, description, and classification, develop some effective simulation methodologies, integrated the model with building energy simulation tools. So that's what, very piece we are working on. And then in the end, we have to demonstrate how these models are useful, how they can they be used in the design, operation, retrofit, by doing some case studies. Yeah. So yeah, so I think we talk about this. This is sort of the framework we're talking about. Yeah. So research goal. Yeah. So I think down below, as I mentioned before, is data collection is very important. So we, one of the big challenges of behavior research is to be able to get a good data set. So the data set we have mostly are from some metering projects and some MMV projects, and usually they don't have good data related to behavior. So they may have very good sub-metering data. They may have very good air conditioning system data. Usually have to do some FDD or diagnostics, but related to behavior, very limited data. And so we're thinking then there should be a better way to represent the behavior, and then how that links to our energy modeling. So we have under the IEA 66, we have 5 subtasks. So on the top, subtask A will look at people's movement and presents patterns in residential buildings, in office buildings. And B will look at the action model in residential buildings. So how people open windows, close windows, and operate blinds, and use air conditioning systems. And C is similar to B, but this will look at commercial buildings, for example, office buildings. And then D is more about we consolidate a model developed from ABC into a module that can be used for code simulation, or can be used to pre-calculate some schedules. Then you can still use that in your traditional tools and modeling. And E is more about using the developed tools to do some case studies, design, operation, or energy management. Yeah. So those are the 2 pieces. And yeah, so I think we can talk quickly about the subtask A. It's about people's presence and movement. So we look at a few data sets, look at, for example, some private office and single occupancy. There's also some open cubicles, look at how people spend. It's quite different. Some people may be more quiet, more focusing on work, so they spend more time in their cubicle, in the office space. Some people tend to be, leaving more often and, talking to others. And so I think those are actually gets very important. If you look at the modeling we are doing right now, we assume every office has the same occupant, profile or schedule. In reality, it's not, right? So I think in the past, maybe it doesn't really matter, but now we have more and more occupancy control system and technology. So be able to model the occupancy accurate. It's very important, actually. I think that actually PG&E is doing this evaluation of VRF systems, right? So if you don't have a better way to handle the occupancy, you will not be able to capture the VRF system's performance, accurately. Because VRF, when all people in the space, you can turn off that system, right? So by modeling, right, you can never show a time that a space is unoccupied. So basically, it's operating like a VRV system. You don't turn it off. Yeah. So I think it's getting more important to be able to model occupancy more accurately. And people's behavior, of course, also depends on whether people in the space. So it's getting. So when we look at the occupancy, basically, there's 4 levels we're looking at. Maybe looking at the total number of people in a building, right? Sometimes you look at whether a space is occupied or not, right? For example, you have some occupancy controls, like for lighting, and sometimes even have some plug loads, and sometimes you look at how many people in the space, like demand control ventilation, so determines how much outside air you need to provide, and the most detailed level is, of course, an individual. So, at a particular time where you are, because you behave differently, you may go to conference room, bring your computers, and so there's certain energy consumption really tied to an individual where you are. Yeah. So I think that is the detailed level. So what we are looking for is, very different levels of question. We probably need different levels of model, because at a very detailed level, you would imagine, in order to have a good model for that, you would have more input, right? At least, and then you have to define, for example, if I ask you, or we want to use this kind of model, I'll ask you, well, what % of time you stay in the office in a typical day, right? And then maybe how much of your time you spend in a conference room, some information like that, and then for, individuals, and then we can be able to develop some models. So subtask B, yeah, so this is being like behaviors, in residential buildings. And so this chart just shows the lighting, so the minimal, when or the probability of people switching on the electrical, lighting. So it depends on the, the light illuminance level and the working plane. So if it's very dark, right, something like, yeah. So for example, right, this is very dark, or it turns it on. But so somewhere here, people will start, turning it off. So it's observing like a typical S curve. And so so this is the subtask B. So try to develop a model, and the model is based on action. So sometimes triggered by you just arriving home. You're leaving, and certain event, or you're going to a meeting. And C is about, so it's dealing the behavior in commercial buildings context. And so that, this is energy use of lighting, per square meter per day. And, so quite interesting is this is a single office, right, single occupancy. So, it is very low. But once you go to like a medium office, many people share, office space. So we would imagine if I'm alone, I don't feel the need of light, I would turn it off. But if I share with somebody, then I don't know whether he needs it, right? And I don't like to ask him every time or every day, right? So I just assume probably he needs it. So basically, that creates much more energy use, which are unnecessary. And so we're also trying to look at, so, commercial buildings, and I think we're talking about central systems, VAV systems, and now going to more with these localized, systems like VRF, fan call systems, which provides more better zoning control. So if you don't need it, you just turn it off. And so the subtask D, so this is what we're trying to do, is basically trying to develop an XML schema so that we have a common standard to describe occupant behavior in buildings, and also integrate all the model we develop, into a software module so that we can use for energy modeling. And so we're talking about, EnergyPlus we're working on. So this test is the tool, the Tsinghua University been working on. We also have people, from design builder team, Chinese, so they all express, certain interest in this area, be able to integrate these tools. So this, this is another graph that shows how we integrate, the tool we develop. So in the end, we want to look at some of the applications. So the same building, but if assume different people or different, family, style live in the same house, obviously the energy use will be very different because of their behaviors, are very different. So we have some sort of, outcomes from each subtask and a standard definition, and basically 3 key aspects we are trying to tackle. One is the data collection. So I think data is the key, right? So we want to basically to look at ask the question at the very beginning. So in order to understand behavior, what data do we really need, right? And how we collect the data, what kind of sensor and technologies. So the first step. And then once we have the data, how we do the analytics, right? There's very complicated stochastic model. There's some very simple, logic, regression model. That, so. And then how we validate the model, which is very important because, I developed this model based on a certain limited data set. But how can I be sure that it also applies to other people, applies to, other location, other country? We don't really know. So that is really, a big challenge. So we have some, international workshops, and in China, we have our first meeting in Hong Kong, and then we have a coming meeting in UK. So I'm one of the operating agents. So we have people from 23 countries. So it has got lots of, interest from international community, and the ASHRAE also. Part of our, it's an organization. IBPSA and the CIPSA are also very interested. So we have a website if you're interested in, our latest news and information. You're welcome to visit. And these are the 23 countries, and this is our working plan. This is so IEA is a very interesting way to work with, because they don't provide funding. So basically, each participant there, you have to find your own funding, get support from your country's representative to the EXCO committee. So that's a challenge. Many people have interest, but may not be able to find funding, or they maybe have some projects, but not directly related to the topics we're trying to tackle. So it's always challenging to gather these 90 people, be able to work on something we all agree to accomplish. So I think we are at the very beginning of this in lots of negotiations. So that's So summary, we know occupant behavior has a great influence on energy, energy use and also technology. And so I think one of the technology example is like the VR systems has been in Asia and Europe for many, many years, working very good. But just come to the U.S. and they don't see as impressive savings. But what they realize is culture are quite different. In Asia, they tend to, if they're living in a room, they tend to turn it off. Here, we tend to forget. And so basically, in order to make it work, like Mitsubishi, they just install an occupancy sensor for the indoor unit. Then it's the same, working with the same in Asia. So, so there's an implication maybe in different culture, different behavior. You need to tweak your technology a little bit, right? I mean, 99.9% is the same. You just need to add an occupancy sensor type. So there's, certain things like that, actually, very interesting. So I've been talking to Daikin. We have projects with Daikin. They're interested in those. So I guess today's challenge you mentioned is, there's no very good methods and common language to describe and handle that. So we're trying to focusing on this scientific framework and allow contribution from, various parties and international, and demonstrate some of the applications in our next 4 years. So what I'm going to show next is there's some real work we are doing at LBNL, in terms of behavior research. So we are developing an XML schema, basically to describe, people's behavior in buildings. So the way we look at that is these, 4 aspects. There's drivers, there's the needs, your comfort needs, your air quality needs, various needs. And if your needs are not met, right, you're going to take certain action, try to restore the need or be able to, adapt. And the system is more like, the building physical systems or controls that you can interact. So if window cannot be open, so there's no way, even though its outdoor condition is favorable, but you can open window. I guess in most of our high-rise building in the U.S. we don't have any open windows, right? Operable windows. Yeah, but in China it's very different. No matter how tall the building, they have operable windows. Yeah. So I think that the design also has some constraint on the people's behavior. So basically, driver represents the stimulating factors that provoke energy-related occupant behavior, and so we sort of categorize in different different groups. There's some building-related, building's property, where the building is located, and some are occupant, attributes, and where the energy attitude, and where the occupant is located at home, at office, and what's the state of the occupant. And it's environmental, it's very obvious, like, climate conditions, indoor temperature, humidity, weather conditions. And then we talk about a system, right? What kind of system, how controllable, it can be, and to allow, enable the, humans interaction. And of course, it depends on time, like, different times of day, different day of the season, can be different. So, and then the needs that represents the, requirement of occupant that must be met in order to ensure, satisfaction within the environment. So there's, physical needs, there's also non-physical needs. And physical needs, so there's a comfort, or acoustic, thermal, visual, indoor environmental quality. There's also biological needs, right? Food, drink, and, all this other stuff. And then non-physical needs, that can be some of the privacies and some of entertainment and other factors. So I think I remember CB's and post-occupancy survey, the biggest complaint is privacy, right? A share office, but somebody make lots of calls a day. So yeah, so indeed, anyway, but it's not directly related to energy. So that this is the needs aspect. And then the action. So we mentioned, actions are interaction with building system activities if an occupant cannot conduct in order to satisfy their needs, right? So you may choose to adjust, thermostat. If feeling too hot, too cold, assume you have a thermostat, and it's real, right? And movement. You may just, too hot and take a break, right? I'm going to somewhere with air conditioning. Yeah, 2 days ago, my office, that's not air conditioning. Outside, it's very hot. Go to conference room, but work there is air conditioning. Yeah, and sometimes, you just do nothing, right? Tolerate, right? But then, sacrifice productivity or, or comfort. And some people may, just call to complain, like co-operators, I'm too hot, I'm too cold. So basically, it's different styles of reaction to if your needs are not met. And the system, so these are all the equipment, all the energy service systems and, different, clothing, cooking, heating, cooling, hot water, lighting, windows, stuff, and plug loads. And so, these are the things that you can interact with, try to restore your comfort needs. So we try to put together these things together, so that trying to develop this XML schema, be able to describe that. And so I think the good thing is then if more people adopt these, when I send you a file, say, well, I have all the behavior described in these schema, and then you open, you'll be able to understand. Because right now I'm using my own language, I'm using my own way to describe these. I think this is sort of in parallel to the building information modeling. So in the long term, maybe this can be part of the building information modeling. Yeah. So it's just a for example. I think we talk about, for example, how we use the framework, like window opening, right? Driver maybe indoor temperature, right? You have some, comfort needs, but if it's, gets too hot, right? So this is feeling too hot, then if your window can be open, outdoor is favorable, you open windows, the system will be window, your action will be, opening window. The needs is your comfort. Driver will be your indoor air temperature. I think another simple is also lighting, right? You need certain light to be able to work. If it's too dark, right? Driver is the light level, and you need visual comfort to provide work. You turn the lights on, and the system will be the light. So sort of based on these 4 aspects, how we can describe people's behavior. And this is sort of implemented as a XML schema. So we're still working on this. Yeah. So let's talk about a few approaches to behavior modeling. So for example, just take EnergyPlus as an example. I think it's other tools, should be very, similar. So we use, schedules, right? Occupant schedules or, temperature schedules and, ventilation schedules, right? And all some predefined rules. Like in EnergyPlus, actually, for example, like shading. So there's 21 rules you can define, when the shade can be, open, close, and 21, but still it's limited to 21, right? Maybe what you're interested is not in the 21. So those, predefined rules, certain limitations. But in EnergyPlus, you also can use energy management system, which allow you to write code. Quite tricky though, right? Like the DeST function, very tricky. You have to spend lots of time debugging, understanding the whole, system architecture stuff. But now there's also search option. If we package the behavior model we're talking about into a software module, and then allows code simulation, through this, functional mockup interface. So it can be used with EnergyPlus, can be used even with your, Excel spreadsheet if you just, want to develop something in-house. And yeah, so also broadly, so there's two ways we model behavior. One is, for example, window opening and closing, right? If you're using EnergyPlus, you define a rule, and the rule is associated with window, right? You said outdoor temperature, indoor temperature, if the difference by certain, right, you open window, right? But window don't open itself unless you automatic control. So the other way to model is we, use agent-based modeling. So basically, each people can be an agent. So you define its behavior. So for these people, right, they will open windows if it feels hot, like outdoor is, 28 degrees, and so something. So you open window, right? So this is more close to reality. Then we can also define people's interaction. If you're alone, or you have to negotiate, this group, behavior. So I think there's lots of interesting work done in this area. There's a professor from Rutgers University also doing some interesting work in this area. So I think going forward, we would like to do more like agent-based modeling, define each people and then put in all the behavior models. And then, we know, these people may, at certain time in his own office, then, how he operates Windows. So yeah, I'll show you some examples. This is a study we did, simple simulation study. So we categorize people's behavior. For example, this is a private office, a single occupancy, where people have different cooling temperature needs, right? So standard we assume 24 degrees, but it's different style. Somebody may have more tolerate, can have it at 26 degrees. So basically, they indicates it can reduce your cooling energy needs. The other way, maybe you need cooler temperature, indicates higher energy needs. And so basically, we categorize these into three, if you will, call it lifestyle. So there's a standard, business as usual. There's an energy wasteful style. There's an energy austerity lifestyle, right? And then you can look at heating, cooling. You also look at the aspect operation schedules, right? So traditionally, this is work schedules, but quite often in office, we are modeling, we assume it's much longer than, and then occupancy control, right? So, it's just based on schedule, but if you want to save energy, right, if it, you're leaving the office, you can turn lights off, maybe portion of the plug load can be turned off, like the monitors, right? You can turn off systems if you can do it, like, a separate system, right? And then the cooling spark control. So this is something very interesting. So we're talking about some of the operation of air conditioning is, you will turn it off when you feel hot. And, so there's a lot of study in China, they survey and do measurement. And so basically when you feel hot, it's like around 28, even, from 28 to 30 degrees. And that's actually higher than your actual comfort temperature. So your actual comfort temperature can be still like 24, 26 degrees. But so, the difference only by 2 degrees. But if you really look at that, that's many, many hours a year. The temperature will be between 26 and 28. So it's a big difference. And then, of course, the daylighting, are you turning off lights, when you have enough daylight? And, and also, for example, in ASHRAE standard, there's a comfort model. So its basic theory is when outdoor temperature gets higher, your indoor comfort temperature is also higher based on some, I think, survey of nature ventilated buildings. But they are pushing these for, mechanical cool buildings too. That's the argument whether that's still applicable. But anyway, if we package all these 3 lifestyle, and then we do a simple simulation. So each one, these vertical, these just, we take the standard behavior lifestyle as the reference. And so, the adaptive comfort, you can say this is only looking at, this is the total source energy. It's in Chicago, so we look at, but basically, right, some occupancy, of course, has significant impact, comfort standard, because you, raise your comfort set point, right? Your cooling stop, we're talking about many hours, you don't really have to start the system. So you take all these together, see, so this can, cut energy use by 50%, this can use by more than 80%, because of the, this is the energy waste for lifestyle. So, its impact is significant. Yeah. And we talk about these occupancy models. Yeah, so we try to develop a module, be able to predict, occupancy. So, you can use it standalone. You can use it to create, schedules. And, I think we talk about it. Let's skip this one. So let me try whether we can, there's a video. Let me see. Where is it? I don't know whether I can show, but it's very cool. Maybe, let me see. Is there
on the bottom?
Yeah, I think that's a screenshot.
Oh.
Yeah, just came in.
I don't know if it's on my machine. So I just have your PowerPoint.
There's an embedded video, so be able to play. Is there?
Bottom left corner there, play button.
Somewhere here, right?
If you go back to the full screen.
Right, somewhere. Oh, that one? This one? Oh, sorry. Yeah. Okay. Let's see. Oh, this is the page. Yeah, sorry, yeah. Sometimes it shows and sometimes it doesn't. But let me see, is it because we need to scroll it down? Yeah, anyway, it's, yeah. Sometimes it's just a click and you will be able to play.
Yeah. Quit out and we see this.
It's here. Yeah. Anyway, so what I'm trying to show is, we have an office with there's a corridor in the middle, and then there's a field office on both sides. We simulate people's moving around, arriving in work, and yeah. So looks like it's not. Yeah. So sorry about that. Yeah. Anyway. So let's see. Now we need to move to the next. Yeah. Yeah. So sorry about the video, but basically, yeah. So our work is funded by Department of Energy, and it's under U.S.-China. It's a 5-year joint research program. Yeah. So CERN also has a website. We've been working on some other projects, looking at building energy data. It's also quite interesting things. We look at. Yeah. So yeah, so that's basically what we are working on. Yeah.
Very exciting.
To be immortalized in the IBPSA-USA newsletter at some point in the future.
So how are you gathering data, or are you doing surveys, or is there any of that as well?
So yeah, so a few things we are doing in order to get data. We are talking to people. So for example, there's a data set we got from Germany. Right?
Yeah.
We are also doing some measurement. Yeah, but it's sometimes quite challenging because this relates to people's privacy, and so for example, even I want to do in our lab, we have to go through a human subject study review, and it takes 6 months to get approval.
Yeah.
So I have lots of data log and sensors. I put it on my office. I don't need to go to review, get all the data. Yeah, but we also propose, writing some proposals and, basically trying to look at better data sets. So you have to start at the very beginning, understand what data we really need. Yeah, but that is a big challenge.
But yeah, we surveyed our own workstations for 6 of us when we realized plug loads alone changed radically. We worked with a tech company and they were doing a little surveying, but I think we're going to do more of that with a few of our clients, just using really cheap little modelets that just gather data, put it on the internet.
Mm-hmm.
It's better than 90.1 schedule.
Yeah.
5% lighting at night never works.
Yeah. Yeah, so I don't know. It's almost like back to square one in some ways. But yeah, there was even a standard way of data we collect in some capacity that could feed into a useful format for this tool. That would be fun to explore.
To try to develop some data collection protocols.
Yeah.
And it's even sensors, right?
Right.
So sometimes you don't need too accurate, or So I think that is indeed very important, because if you don't have a good data set, you cannot have a good model, and then you cannot validate the model.
So is your focus going to be on 2 building types, residential and
office
buildings? That is your, and what do you envision as the end product? Like, do you envision a library of?
So that would be like we would, part of the Annex would have a data collection protocol, right? Mm-hmm. Just focusing on behavior-related data, and then of course that includes how we should design the experiment if we want to do this kind of research, and then once we get the data, how we do the analytic, right? How we do the modeling, we develop a model, and how we validate the model. This also needs to be approached, right? Because return behavior is not a deterministic step, right? You cannot just compare the differences. You may have to look at from the stochastic, from the profile, from the probability perspective, and So and of course at the end we would develop the tools, right? So for example, if you do energy modeling now, you can look at like different people's lifestyle, right? You can evaluate the impact of these lifestyle energy use. I think a particular interesting point is also evaluate the technology. So some technology may very robust, no matter what kind of lifestyle, what kind of people, what kind of behavior, right? But some may be very tied to people's behavior, right? Like nature motivation. You let people open, closing windows, right? But you don't know people behave so differently. So I think the idea is, when we evaluate technology, we should at least do these like 3 scenarios. Assume this is the traditional way of doing it, but how about another lifestyle, right? More care about energy. Is another, don't care about energy. So you want to look at technology that very robust, very consistent savings, performance.
Right.
Some technology very picky, then you may have to be very, very careful because you don't know the reality, who would actually live and work there. Right. So I think that there's a risk. Basically provides a tool. You can evaluate the risk associated with the performance of technology because of the human, behavior.
Right. And the 23 countries who are participating in this program, is the intent, and maybe you haven't figured that out yet, but is the intent to develop these models for each countries or each culture types, or like is it going to be subdivided, or is it all going to be like consolidated into one set and averaged out, or like what's the?
No, we want to keep the variety. So basically, So it's a good question, because the real question is, are the differences between countries, more significant than the differences between individuals? We don't know, but because within the same country, right, we have so many different people, and you have men, women, and different ages. They all perform very different. So that is a good question. But I think the intent is not to categorize behavior by country. It will be based on the actual pattern of behavior. Yeah. Like, take an example, like, when opening windows, right? One certain time it depends on indoor temperature, right? The other may depend on, CO2, in space. And maybe some would depend on personal habits. The people arrive in the office, open windows for 30 minutes. There's no reason. Right. Always doing that. Right. It's personal habit. And maybe some are based on other noises and yeah. So we try to categorize. Yeah. But again, I think we would have to based on real data. What data tell us? Right.
Are you looking at age? Sorry. Go ahead. Are you looking at age also? Because age typically have a major factor. So you're going to categorize by age?
Yeah, so I think in residential, definitely, right? You're looking at, young adults and teenagers. They, compared with senior, of course, they all have very different, comfort, temperature needs, and, of course, and the way they like, taking a bath in teenagers, right? And I don't think how much more water they use, right? So I always try to convince my son to take, shorter shower, but as you imagine, he don't even understand why I need to take shorter. Yeah. But that's a significant factor. And I think there's I saw some studies look at some, like senior housing. Actually, they use quite significant amount of energy. Not necessarily.
They like it warmer.
Yeah.
Typically like 75 or so at their comfort level.
Yeah. Or maybe they don't know how to, control, adjust the system.
I think they get thinner as they get older, and then they get more susceptible to
Yeah.
cold.
Definitely higher, sometimes up to 80s.
I mean, you might even find that like radiant surfaces are a better application for senior homes because it radiates heat instead of air conduction. So it might be a different design. Like we just going back to plug loads on a high-tech or an office park, lobby for heat recovery to go into the design because their plug loads were high. They had a lot of people. If they have goals of going to tablets and having like less staff than they normally have in office spaces. So to continuously reduce their energy bill, if they didn't have a vehicle to like capture heat, right now it looked like a great idea. No heat recovery will save millions of dollars. But in 3 years, if they didn't have it, they would have to use those heat because that was their system. So it's like, what's robust? Like where are you headed?
I was wondering, you showed early a big spread in EUI, for buildings, and that there are lots of factors. Has anybody tried to study how much of that variation is occupant behavior versus, differences in design or, operation? Wondering how big a piece of the pie.
Yeah, exactly. Yeah, I think that. So it's good. Yeah, we have done some studies. Yeah.
So that goes back to the house example, right? Or the apartment. They're the exact same spaces, but then the occupancy is like what they're different in energy.
Yeah, that would be one example where it's probably behavior, although it could be broken air conditioners in some of the units too.
Yeah.
But we've run into even a different problem where it's not necessarily the occupant behavior, it's the policy or the administration behavior. So if they say, we decided that we're at 62 year-round no matter what. And so the occupant doesn't really have anything to do with it, but I don't know if you'd lump that in with occupant behavior, or if that's something that's doing it.
Yeah. So I think, so basically there's something occupant can control, but it's certain things like operator or facility managers, right? Yeah. So, we sort of try to differentiate these, but they are, there is important because for large building, you tend to have more central controls and systems. So how they operate the buildings and that's important. And even maintenance, right? How you weigh or how frequent you change filters. I mean, it's also energy implication, and it's also indoor air quality, much more important than energy as well. So I think the other, so besides energy use or energy efficiency, we've been thinking about actually in a demand response is also, very interesting related to behavior. So for example, like now we have to cut oil electricity use by 30%. I think if you ask people, people will give you very different options. For me, maybe I'm very sensitive to temperature, so don't raise my cooling support. But you can dim my lights, I'm fine, darker environment. But other people, maybe differently. Maybe one care, very, very sensitive to outdoor air, so you can also cut outdoor air. The other one, maybe it's fine, just turn it off. So I think actually it relates, to people's needs, health, factors as well. So how you do the, the demand response. Because now we're doing, okay, let's just cut lighting, dim everything, let's just raise the water temperature. Right.
And Jonathan, have you guys looked into the search or predictive algorithms that the big data companies use? I mean, look, like for example, those companies, they predict what we do on internet, right? Mm-hmm. Go to Facebook, they know, what people can search for, or they give us options. If you go to shopping, so they know based on what we do, right? So something like same on similar patterns. If you look into what they use for, because it's all human interaction with computers and then with buildings, right? Yeah. So how they tackle this problem or this issue of human interaction and how they predict what they will use, they can help a lot in kind of streamlining the approach, right?
Yeah. So I think that So
for example, like if you have one building in China which is super smart and everything is can be monitored, and then on all 23 countries, then you can have a pool of those measured behavior patterns, right? And then just a thought.
Yeah. I think in this space, like retail, like Walmart, they spend lots of dollars in looking at it. They collect lots of data. Yeah. There are lots of cameras everywhere, and then they're looking at where you stop the most time, what you purchase, and there's a lot of data mining.
And then in the end, like every person will have a portfolio sort of an energy behavioral portfolio sort of thing.
Yeah. So there's always argument provide energy information to individual. Would that help? Right. So I think now we even PG&E, right? You get a free energy report. Compare with your neighbors or compare with your homes. Right. I don't know. How that really help. Maybe you feel good if you're top tier. But
So jumping off that, I think probably one of the biggest people out there that understand people is Google, and their nest on the wall right there. That's
why they go.
They understand more data to reverse engineer building performance. The times are changing for sure. You can leverage what they already know.
Yeah, that's what I'm saying. I mean, if you have some really smart buildings which all with meters like this or nest things, and we can get all the data. And we can streamline the process.
Yeah.
Right.
So I think that there's some studies looking at people's occupancy, right? Because smartphones, the wireless connections, routers, and they know where you are basically by digging into those data.
I mean, it's not that far-fetched at all. iBeacon's doing the exact same thing. It's trying to track every phone that's trackable walking into a door and following it around for a little while to see where it goes. So I think that you could do the same thing. I don't know about the plug loads, like you were saying. You got that sort of thing in line with telling you what it is.
Well, you could do it with phone, but there's also, I mean, I could even see this going another direction with people building robotics that are adding elements to buildings that just allow more control at every level of occupants, whereas they do traditional VAV control. But I mean, if this was sort of, I could see this building to a case of if we want to hit net zero as a state, maybe if you have an air-based system in this sort of building, you need to have an occupant ability to control their own environment in order to save energy, or in order to be robust enough to, in any mode of operation, be a low-energy user.
There's also a psychology aspect of that. If you give people, more control, they feel good, so they be more tolerant or be more understanding. Simple psychology factors as well. Even provide a fake, thermostat. That's good, not open. Yeah, quite interesting. Yeah.
Has any of your research led to any, like, you having any suggestions about maybe what, or observations about what, like, what behaviors might contribute to, like, highest energy usage, like, in their variation, and, like, maybe what you could recommend for occupants, like, for building owners, or for anyone to recommend to occupants what they could do to, like, have an impact on reducing their energy usage?
Yeah, so there is a research proposal we just submitted. Yeah, yeah. So yeah, I think, but I think it depends, right? You know, depends basically the context. You know, what kind of buildings and where you are, right? What kind of systems, you know, what climate. Yeah. So, and I think also depends on what are the things you can really control. There's too many things we would like to, but we don't. Right, like in office, right? Most of time, you know, you don't have a thermostat to control your temperature, right? And so yeah, so there's a limitation to that. Yeah, but I think by providing better information to occupants, you know, there's an opportunity to save energy. Because when you're talking about, like, you know, a little bit of change behavior, they will realize, well, this will sacrifice my comfort. Not necessary, because we know, right, you know, to meet the comfort, there's too many ways you can reach there. And of course, many ways can be more energy efficient, right, than the traditional way we you know, talking about. So we you know, as part of this you know, sub-project, we compare buildings, you know, in China and the U.S., right? So, you know, here we have 90.1, Title 24, very stringent, you know, everything is, you know, very high-tech stuff, automatic controls. So in China, you know, they're lagging, like, you know, in terms of building technology, actual application maybe by 10 years, right? So, but if you look at the real energy use, they are not bad. They are actually better than us. So HVACR has a scorecard, you know, ranking by different sectors, building, transportation, and, you know, so buildings actually China is the best, but they don't have the most stringent curve of technology. So basically, what's really going on is the way people, you know, use buildings or, you know, operate buildings. So here, you know, we tend to in operate building in a mode we call full-time full space, for the concept from Professor Jiang. So basically, condition our building much longer. How typical office buildings start at 6 a.m. or even 5 a.m. all the way to 10 p.m., right, much longer. And then we condition the whole building, even though many conference room offices, they are not occupied, right? And then China tends to operate differently. They call it part-time, part-space. So they operate in a much, you know, short time, you know, when people in a space, they have the services, and when, you know, a space is occupied, they will have the services. So this difference is much bigger than the technology difference. The chiller COP from 5 to 4.5, much bigger. Yeah, so I think we're also trying to learn from the Department of Energy's perspective to, you know, learn these kind of differences, because not everything needs to be handled by technology. It's also, you know, operation, you know, people's behavior too. Yeah.
I was just curious, building on that, are there, as you see changes in affluence in countries like China, do their behaviors become more wasteful, more like ours in this country, or are they retaining their more efficient behaviors?
Yeah, I think definitely there's, you know, there's that risk or there's the trend. So, you know, I think we have conversation in the afternoon. So China has this Yangtze River. So the north of the Yangtze River is like a cold region. So, you know, by law, they would have heating service during winter, and these are mostly district, you know, central heating. So they would actually, you know, start the central heating, like, you know, starting November 1st or mid-November all the way to March, you know, mid-March, right? And then people to the south of the Yangtze River, they don't have heating at all. You know, actually it can be just difference by 5 degrees or something, but it's not heating at all. And then, so I think to your question, then people have more income, you know, living standards higher. They would buy, you know, those portable heaters, right? They would, you know, they want to improve comfort. So I think that will create a challenge on China's energy, you know, infrastructure energy use. So China, of course, have their design standards like ASHRAE 90.1, but they realize the design standard does not really cap your actual consumption because we're talking about a formula, right? It's energy service divided by energy efficiency. If you just focus on energy efficiency, forget it's a numerator there. We're getting into trouble. So they are developing a separate efficiency, the standard called energy consumption standard, and it's based on actual energy use. So they survey thousands of buildings in our country, and then they put everything in a profile. They determine two values. One is they call it restricted value. So if your energy consumption is higher than that, you have to do something retrofit your building. Otherwise, you get fined or put in jail or something, right? China could be very tough on this, right? So it's not really related to how the actual, the dollar amount of the energy, their policy. And then the other, they call it target, target EUI or something. And that's, they will promote if you reach that better than that, they give some incentives. And so they realize that is the only way to cap the real energy consumption. So they have that standard. Yeah. I don't think we can easily do that here.
Years ago, I met some guys from Singapore, and they were talking about making requirements for people to retrofit their buildings. And I was saying, well, you can't do that, by policy. If we tried to do that here, people would, go crazy. I said, oh, yeah, sure we can. We tell them to do it. Well, thank you.
Yeah.
Sure.
I do have more tidbit that might help. I know that you were talking about commercial buildings, lab buildings. My firm does a handful, but does a lot of lab buildings. And so there's three groups. One's called I2SL, which used to formerly be Labs 21, the International Institute for Sustainable Labs. And they've been trying to benchmark labs for the last 20 years or so. And so they're actually trying to collect the data that you're trying to find from labs. The next group that's trying to do it is a group called My Green Lab. Get past the kitschy name, and it's actually a substantial group. They're very new. They've only been around for about a year and a half, but they're actually trying to do the exact same thing. But they're trying to work with the manufacturers of the equipment that draws the plug load to try and get their numbers from it. So they actually want to know the difference between like a -80 freezer and a -70 freezer and what that draw is. So they're getting a little bit more fine grained, but they might have the data for it. And then the third one, I'm just forgetting, is Genentech. So Genentech down in South San Francisco actually pays employee bonuses based upon energy use in their labs.
Really?
They incentivize lower energy use from labs. So literally, if you turn off the lights, you're making a dime every time you walk out.
But you cannot perform work, right?
Well, that's what they're trying to find is Genentech's using this as an incentive to try and baseline their laboratory users to say, what do you really need? Are we overproviding? Are we underproviding? If I give you $100, will you turn the lights off more than you need to because I'm paying you to do it? Or will you still do it just the right amount that you need to? Anyway, I don't know what kind of benchmarking they have, but it might be three groups to chase down that would provide some sort of benchmarking. If you're going down that lab route, if you're trying to stay in an office building, it might not help. But although they're doing, I know Genentech's doing it for their office wing, all the administrators the same way.
So what we are trying to do is also, I think we have a coming seminar at ASHRAE, Seattle. So we have a panel, I think, 4 speakers to talk about, behavior-related research. There's a professor, from I don't know, you may know him, B.Eng from Tsinghua University of Denmark. He's actually one of the VP of ASHRAE. And then it's this Professor Clint Andrew from Rutgers University. And then Professor Darzong from Tsinghua University. Myself, we're talking about trying to have some noises in ASHRAE. It's very different, But we also, part of this, every year we also have a one-day workshop. So we invite people, mostly from industry, to talk about some of the challenges. And we actually inviting people from Google, Facebook, to talk about how they use our searching data, figure out our behavior. So on August. So I'll see if we have a lot more people. I'll send you information on that. But there's lots of interest, but quite difficult. For example, I think one of the questions you asked is, right, if we figure out all the behavior, in the end, I think we need something like this, right? A device, intelligent, that learns your behavior, right? And then feeds back to a control system. So the control system knows, okay, those are like, comfort you really need, but you don't have to always behave that way. Then you can advise the occupants or the operators in a positive way. You can operate this way, still provide same service, same comfort. So actually, that is an area we are trying to develop a proposal with Siemens, trying to get things and tie to some, intelligent controllers and be able to demonstrate this kind of technology. But I think the next. Sorry, go ahead.
No, it's great. I mean, it would save a lot of money in construction. I mean, again, on big campuses, when they have to go to calibrate all the controls on every side of every building, and if it is itself, when you have one sequence, it's that's a lot of money.
I think with all the computer stuff, that's more, more than enough for us to do this kind of simple things.
Cool.
Sure.
If anybody's going to Seattle for the ASHRAE meeting, remember there's an IBPSA meeting.
Yeah.
Yeah, IBPSA-USA meeting on Saturday before the ASHRAE.
We work with Nakamura. I know he's doing a similar program.
Yeah, thanks for coming.
Thank you.
Yeah, thanks everyone on the line.
Well,